So there's a guy pretty awesome. Not no, there's a guy and you know Gary. I'm not. I don't think that they're going to stick against them.
I was at like 3 the whole weekend.
For sure, you just go. Twentieth is Ivy Day.
Right. Your quiz is going to be tomorrow. You'll get to use your calculator, but I'm going to be asking that you show all your work. And like I said, you didn't have a calculator, so there's some multiple choice on the quiz, but I'm going to ask you to show your work despite the multiple choice. Okay, so, but that also allows me to assign partial credit even if you get the problem wrong. So I'm going to require you to show your work just like how you've been doing on your quizzes. I'm sorry, on your reviews. There's a mixture. There's a mixture. Yeah. Now, having said that, there are some problems that you'll be specified. Hey, do test the convergence or divergence using this particular test. But then there are also other ones that are open-ended, and then you can decide which one you want to use. And then there are some problems that you can get to the solution through multiple paths, right? You can use LCT, DCT, or even geometric series test. So, I think hopefully with the practice that we're getting, that you feel comfortable being able to kind of go down your list of options and hit the appropriate convergence test. Yeah.
Next question.
11. So most of you guys have worked through worksheets 1, 2, and 3, which is great. I think that's a great way for you to study. I also have the other set of worksheets that I gave you. Some of you guys have been working through that. Just be forewarned that some of my solution keys were not checked very well, and so there are some mistakes in there. So if you're wondering whether you're doing something wrong or whether it's the key, and if you get stuck on the problem, feel free to send me a text remind this afternoon or evening as you're studying. I'll be able to respond to you. So sorry if those are not fully correct with the solution key. Some students were asking for additional review, so I'm printing out some additional just practice that I found on the website, on other websites. So I'll have that available if you want just additional practice tonight. Okay, help sessions. I'll have one this afternoon and tomorrow morning, 7:15. Just if you want me to go over those additional worksheets or worksheets 1 through 3, I'll be available for help session this afternoon and tomorrow. All right, any questions about your quiz tomorrow?
No, sir.
Okay, so I want to go ahead and get started with the next section. This is going to be the last set of new topics. So you see that we're going to be starting our test review next Friday. So, we only have, 6 days of new materials, new content left, and then we can kind of begin shifting over to review. This is going to be the first day of our test review, and then the test won't be until the following Thursday. So we're going to have 4 full days to do a test review, right, for our test over new content. Okay, so if you guys have your calculators, that'll be really helpful. But let's look at page 1. Oh, I realized after creating the packet that I left out a page. So this is page 2B. It follows page 2. So it just yeah, I got the pages mixed up. But I think this is also a good thing having this loose leaf sheet because on the back, oops, did I put that on your back? Yeah, so on the back, I have some helpful summary of formulas that we can use to reference as you're working through the rest of these new topics. So, okay, so sorry about that page out of order, but it also is a good reference sheet for the back page. So we have something called the alternating series error bound. This is a topic that we're going to refer back to at the very end of our new topic called Lagrange error bound. So they're very much related. We're doing the easier of the two right now. So the idea is how accurate is our approximation, right? So we're going to have these partial sums, right? A partial sum, we know that the more sums that we add together, the more accurate we're going to be, right? And so partial sum 5 is going to be better than partial sum 2. But the question is, how accurate is our approximation? And that's what the error bound is doing. It's just allowing us to kind of give us a safe upper bound in terms of the accuracy of our approximation. Okay, so in order for us to do this alternating series error bound, though, we must have a converging alternating series. If it's a diverging series, then we're not able to apply this error bound. Okay, now this is going to seem tedious, but I think this is going to be helpful for us to kind of see the big picture here. We're going to find the terms. So a sub 1, a sub 2, a sub 3. And after you do a couple of them, I can start filling in the blanks for more of these. But let me just do a first few here. So if I want to find the first term, okay, I'm just going to plug in whatever my lower bound is, right? So my lower bound could be starting at 1, it could be starting at 2, it could be starting at 0. In this case, starting at 1. So if I insert 1 in for n, what is my first term going to be? Yeah, the first upper numerator is going to be positive. Denominator is going to be just 1, so just 1 over 1, which is 1. Okay. Next up, if I plug 2 in, negative 1/2. Okay, so on and so forth, right? So I'm going to just go ahead and start filling this in. Okay, we're just finding the nth term of my alternating harmonic series. So first off, do we agree that this is a converging series? Yes. Yeah, this is it'll pass both conditions, which is the limit of my 1 over n approaches 0. We know that's true. And a sub n plus 1 is less than a sub n. Okay, we know this is a conditional converging series, right? Without that alternator up top, we know this will diverge with harmonic series. Okay, the decimals, I think it just kind of helps give us some additional ways to explore. So I'm just going to write down the decimal versions of those fractions that we found. Okay, so next, we're going to find the partial sums. Based off of what we see from our series. We'll just do a first few and then I'll fill out the rest of it because as long as we know how we're getting to those values. So S of 1 will go here. S of 2 will go here. S of 3, S of 4, so on and so forth. So S of 1 just means we're going to add just the first term together. S of 2 just means we're going to add the first two terms together. S of 3, first three terms. Okay. So S of 1 which is it's just what? 1. S of 2 is 1/2 because 1 minus 1/2 is 1/2. S of 3 is 1/2 plus 1/3. Right. Okay, so we understand the process, right? I'm just gonna go ahead and just fill out the rest of this for us. So 5/6 minus 1/4, 7/12. Skipping all the busy work, but we know how we can get this, right? I think having the decimal version is going to be helpful. So I'll put 1, 5. Okay. Okay, now the idea is that the more partial, the more we are, the more sums we're adding together, right? The higher the partial sum, the more what our sum is compared to the actual sum. The more accurate, right? The more accurate we're going to be, the more terms we add together. Now we're going to plot these partial sums on this graph. And we're going to see kind of what patterns we see from this partial sum. So that means with the first term, my partial sum is 1. So I'm going to put all the way up here. And we're just doing an approximation, right? Second partial sum is going to be at 0.5. Third partial sum, 0.833. Just going to make your best approximation here. Fourth partial sum, 0.583. Fifth partial sum, 0.783. Point 616. Point 759. If you had to guess, where do you think the actual sum is going to end up being? Yeah, around 0.7, right? So the idea is that this partial sum is going to keep flipping back and forth, right? Keep bouncing above and below that actual sum. Obviously, as we approach infinity, it's going to eventually reach that sum, but it's ultimately getting closer and closer, right? So now, normally we don't know what the sum of the series is, okay? But in this case, we do know there's a proof behind it, but we're not going to worry about it. The actual sum of the series is natural log of 2, which is around 0.6, oops, 0.6931. Like you said, 0.7, really close. Okay, so I'm going to just draw a red line to indicate where that sum is. We can tell that we're getting closer and closer. Okay, so this partial sum will keep alternating and bouncing above and below the line until eventually that partial sum approaches that natural log of 2, which is closer to the line. Okay. So I want us to explore the accuracy of our partial sums compared to the actual sum, okay, just for demonstration purposes. Now, normally, you're not going to have to worry about, wait, what is the actual sum? That's not going to be the purpose. Okay, so just in this case, we're just identifying the actual sum to give us some just as part of a learning process to see where we're kind of headed. So the error of the partial sum compared to the actual sum, this is the actual sum value minus the partial sum. We're just trying to find the accuracy. How off are we from the actual sum? So if I do S sub 1 or it doesn't matter which order I subtract, I just care about the positive value, the positive error here. So S minus S sub 1, which is just basically natural log of 2 minus 1. The natural log of 2 is the actual value. I'm going to get 0.3068. Okay. And then our error should become what as we move on? Yeah, good. Okay, smaller and smaller, right? Okay. So I'm just going to fill this out for us. So by the time we get to the 8th partial sum, our accuracy is going to be pretty good, right? 0.0586 off of the actual sum.
There'll never be a time where that error gets to 0.
Technically, it will, because it's the idea that infinity will eventually reach that sum. But for our purposes, right, anytime we can come up with a number, actual number, is always going to be more than 0. But the idea is that, yes, it will eventually hit 0. Now, our goal is we don't really care about the actual error. Okay, that's not our purpose. Our purpose is, can we find a convenient way to point that we're doing this. The whole point is that our error is actually going to be a pretty good approximation if we just look at the next term. All right. So what's the next term in our let me see here. Okay, so our next term is, for our first partial sum, the next term is 0.5. Okay, so our error is actually going to be guaranteed to be less than the next term. Right, you see that 0.3068 is less than 0.5. 0.193 is guaranteed to be less than the next term here, which is 0.33. Okay, so that's really the benefit of this alternating series error bound, is that if we want to figure out the accuracy of our fourth partial sum, we can just look at the fifth term, and the fifth term will give us a good safe boundary of how far our maximum error is going to be. Okay. Again, we never have to worry about, wait, exactly how accurate our partial sum is. We just want to find a safe upper bound. If we just look at the first unused term, then we can get that safe upper bound. Okay, so here is the note that, or the definition that we want to put down here. So if you have an alternating series that converges, so that's important, we can approximate the sum of the series. So S minus S of n, this is the actual error between the actual sum minus the partial sum. Could be the fourth, could be the fifth partial sum, could be the sixth partial sum, is equal to my R sub n. So my actual remainder, which is my error. Now, we don't care about, for us, we don't really care about what the actual error is. We just want to find something that is a safe upper bound. So we can guarantee that our remainder of our partial sum, or the error of our partial sum, is going to be guaranteed to be less than or equal to the first unused term of my sequence. Notice that we didn't say the error bound, right? It's the error bound is the next term. So that's a really convenient way for us to be able to identify the accuracy of our partial sum. We know that our partial sum is going to be no worse than whatever my next partial sum is going to be. Okay, so error bound is the boundary or the worst case of how far off your actual error is. It's a safe estimation of our error accuracy. Okay, is that making sense so far? All right, let's go to the next page here, page 2. We start off with 3 and 4. I think those are more straightforward, and then we can come back to 1 and 2. So this is a calculator active here. It says approximate an interval of the sum of the series using the alternating series bound for the first 5 terms. So we want to use S sub 5 to figure out how accurate our partial sum is, because we know that our fifth partial sum is not going to be as accurate as the actual sum. So if I want to find the fifth partial sum, we're going to go to math 0. And we're just going to enter in our series here. We'll just go from 1 to what? What's our upper bound going to be?
5.
Yeah, so we're just going to add up the first few terms, making the calculator do it for us. So we're going to go from 1 to 5. Now use your x as your variable.
I put in decimal form of fraction.
Fraction, yeah, so I'll do alpha. Oops. Not getting the form right here. Yeah, let's do decimal, sorry. Okay, did you guys get 3.354 repeating? Anybody have questions, have issues getting? So once you get your fraction to show up, if you do math and then select the decimal version, 3.354. Okay, so we know that this sum is going to be off of, it's not going to be the exact value, but we just want to know, what can we say is a safe boundary of our partial sum. So our partial sum here is a convenient way to test or the accuracy of this fifth partial sum is simply to look at what? The sixth term. Yep. So let's find a sub 6. The absolute value of it, because okay, so how can I find the sixth term?
Plug in 6.
Yeah, plug 6 in for n, and whatever number we get, that's our sixth term. So I'm going to get -1 to the 6 plus 1, so that's -1 to the 7th. That's going to be negative 4 over 6 squared. But it's absolute value, so it'll be turned back to positive. So we know that this sum is going to be at worst off by 0.111 repeating. Does that make sense? Okay. So it could be less than 3.354 by 0.11, or it could be more than 3.354 by 0.11. But we know that that's a safe boundary, right? Our actual sum is going to live somewhere between this plus or minus this. So the actual sum is going to be 3.354 plus or minus 0.111. Now, if we were to get a higher partial sum, then what would you expect your error to be? If this was like the 7th sum or the 8th sum,
It'd be less.
it'd be less, right? So, the more partial sum we get, the tighter our interval will be, right? If the less our partial sum is, then there's going to be a larger error bound, right? Okay, so we can say this: our sum is going to be so 3.354 minus 0.111. And then the largest that the sum could be is 3.354 plus 0.111. I mean, our sum is already pretty accurate. It's accurate to 2 decimal places. It's just that third decimal places is not defined. Yes, question. Yes, well, yes, it only works on alternating series. At the end of next week, we're going to talk about What if it's not an alternating series? If it's not an alternating series, we can still create some sort of a error bound. But this is the easier one that we're talking about. But to answer your question, yes, it can work for non-alternating series, but the formula is a little bit different. But it's going to kind of follow the same idea. We're still going to look, it's still going to involve the next unused term with slight variations. So we're kind of learning the foundation of the error bound that we're going to be studying. Okay, let's look at number 4 here. So let's say we have a series. And with the first few given terms here that they're spelling out here, show that 1 minus 1 over 3 factorial approximate f of 1 with an error that is less than 0.01. Okay, so 1 minus 1 over 3 factorial, this is involving how many terms here? So this is basically saying how accurate is my S sub 2 partial sum compared to the actual. Now, we're not going to know what the actual is. We just want to know how far off our partial sum is. So we can say absolute value of S minus S sub 2 is guaranteed to be less than or equal to what? A sub 3. Yep. That's it. So whatever that first unused term is, my partial sum is guaranteed to be no more, or it's not going to be off by no more than what we see with our third term. Okay, what's my first unused term? Or what's the third term? Yeah, and I can replace the x with what? 1. Yeah, that's my x value. And let's see, is this value less than 0.01? So factorial is located under math, probability, PRB, and then that fourth option then. So math, scroll over to PRB, probability, factorial. Sorry. One over 24. Oops, sorry. 5 factorial, my bad. 1 over 120, which is 0.0083. And we know that this error is definitely less than 0.01. So we can say for sure that this partial sum is going to be guaranteed to be less than 0.01 because we know it's going to be less than 0.0083 in terms of how far off this is compared to the actual sum. Okay, so that's really the big idea here is that if we want to figure out how accurate our partial sum is, look at the first unused term, and that's going to give us a safe boundary in terms of how accurate our approximation is. We're not concerned about how accurate our actual approximation is. We just want to find a safe upper bound. An easy way to do it is to look at that first unused term. Okay, you come up and get your phones. I want to see if I can get that additional worksheet for you guys to pick up.
The oven.
That's one. Yeah.
Oh, you didn't.
Yeah, I that's walking. And so obviously, I got like half of that. I got so lucky. I'm like, wait, I'm like, I'm gonna do my homework tomorrow for tomorrow night. I'll do my. I don't know. I will be doing. Yeah. That's the entire. All the time.
You know what's really funny about you know what's really stupid that my brother is going to be doing an internship in Chicago, and so he's not gonna be there. Yeah, I'm just gonna be let loose in Boston. Yeah. I cannot like oversee. I went to Kroger, I feel like
It starts snowing.
yeah, yeah, but it's like really hot in Boston, but it's actually better than it is. Or just, it's like.
Additional practice worksheets if you want to, for your test review.
But yeah, I'm kind of disappointed because this already, I know. I have no. No, it's already.
I think the best, having a worksheet. That's gonna be the best.
But my brother's not gonna share. Not go with him.
We gonna show you. Okay. Yeah.
I love Tucker. He's gonna be, what is the process? Oh, really? Thank you so much. Thank you so much. He's like, that.
I think I'm fine with everything. I just look decent and also. And I don't think there's another. So
So basically.
It's only diverging when you assume. That's the only time you'd ever like say additional.
I think I'll show you one.
Or like.
The most thing.
Show my worksheet. Thank you.